Right, good afternoon, everybody, and welcome to this week's deep dive, where we have a very, very interesting and what I believe to be a very important topic for the future of both medicine and hematology, and that is hematology and artificial intelligence, an overview of current applications and future potential. And I'm sure many of you have already had exposure to many of the current AI applications that have just been coming in like waves, one on top of the other during the last 2 or 3 months. I'm sure many of you have worked with ChatGPT or GPT-4, Midjourney and DALL-E and all these other interesting applications. We now have all kinds of text to image, text to video, as well as vision-based machine learning applications that will in the future make a big impact, we suspect, in the pathology sphere and in the hematopathology sphere. AI modalities that can work in a way to predict diagnoses and outcomes. And I'm very, very interested and excited to hear what Professor Jan Gertnel will share with us today. Before I introduce him, let me just remind you that all the Monday afternoon sessions are recorded and can be found on the Blood SA Foundation website, as you can see on the screen, under Resources, Deep Dive. Please feel free to go and have a look. There are fantastic things that you can use for training of, for yourself or for your trainees if they were unable to be here or if they are new. There are a lot of historical sessions there as well. Please take part. We say every week, this is like a bring and braai. We all try to contribute, make a comment, ask a question, say that you like it, just do something. You can do that in the chat box, you can do it live, but let's really make this an opportunity to make this a joint collaborative team playing effort. CPD points are automatically submitted to the Health Professions Council for all those registered in South Africa. What you do have to do for that, though, is stay in the meeting for at least an hour. That's an automated system, so if you're not here for an hour or longer, unfortunately, that may lead to no CPD point being allocated. For those from other countries, welcome. If you need CPD certificates, you can email Melanie Davids at the address on the screen, and we can provide you with something in a PDF format. This is our team of organizers, and I want to give special thanks to the team leader, Professor Estelle Verburg, Dr. Gerdien Kritzinger, who is the Blood SA National Training Coordinator and does a lot of the organization behind the screens and also sends out the nice invites, and Mrs. Melanie Davids, the CPD administrator of our department. So, as mentioned, today we speak about hematology and artificial intelligence. Next week there will not be a deep dive, just take note, it will be a public holiday next week, Monday. So if you come, you will have to make it a nice meeting amongst yourselves, whoever pitches up, but there will not be a lecture. So without further ado, great for me to introduce Jan Gert, who I've known for a very long time. I was fortunate to spend a few years in Bloemfontein. I think Jan Gert and I shared at least 4 or 5 years there when he was a registrar in hematopathology. Somebody with an incredible heart for patients and a passion for his work. And it was a wonderful discovery that he is also interested in AI. And Jan Gert, really great to see you again virtually. And thank you for agreeing to talk to us today and for taking the effort to prepare this talk. We're really, really excited about it. So with that, thank you also to everybody who is sponsoring Blood SA and the deep dive. We really appreciate it. And here you can just see that we've got the full support of the South African Stem Cell Transplant Society, of SACHAS, the Clinical Haematology Society. It's great that this is really a true team effort. This deep dive is not the property of any particular university. It really belongs to all of us. So make the best of it. So with that, I'm going to stop my screen share and over to Jan Gert. Jan Gert, you are welcome to jump in at this point. Sorry, I couldn't put my video on while I was sharing, but there we go. Over to you.
Just give me a few seconds. I need to just get back into where I was before we started.
I think I failed to mention one of the most important parts, and that is that Jan Gert is a professor in hematology at Tshwane Academic Division of the NHLS and University of Pretoria. So Jan Gert, also congratulations on your promotions. It's really great to see you fly.
Good afternoon, everybody. It is a privilege to be here. Somebody that I've known for many years, and incidentally is the way I ended up in hematology. Vernon, you're a big part of my story. It's good to see everybody. Okay, so I'm going to start off by saying I truncated the title a bit, took out the future and focused on current applications of artificial intelligence and machine learning in hematology. So we all know that artificial intelligence is a tool in the ward and in the diagnostic laboratory. It is supposed to represent an aid to clinical and diagnostic practice. Today, I'm going to highlight a few aspects of this phenomenon, and this is there to help us to improve our collective practice in our quest to improve patient outcomes. The purpose of my presentation is not to change all the attendees into computer scientists that know and understand the intricacies of artificial intelligence and machine learning, but merely to aid and to change the participants into informed consumers that know the strengths and the limitations of artificial intelligence and machine learning. Several stumbling blocks that are currently prohibiting the wider use of artificial intelligence in healthcare, some of which include data quality and access to these data sets. And one of the major challenges of artificial intelligence in healthcare is the quality and availability of data. In order for AI to work effectively, it requires an access to large volumes of high-quality data. However, many healthcare organizations struggle with data silos and that leads to the lack of interoperability and data privacy concerns that make it difficult to access and share data across different systems. Healthcare is a heavily regulated setup, and there are many regulatory challenges associated with the use of artificial intelligence in healthcare. For example, the use of artificial intelligence for medical diagnosis and treatment must comply with strict regulations and standards to ensure patient safety. Artificial intelligence raises a number of ethical concerns in healthcare, such as the potential for bias in algorithms, privacy concerns, and the potential impact on the doctor-patient relationship. There's also a shortage of artificial intelligence experts with specialized knowledge in healthcare. This makes it difficult for healthcare organizations to develop and deploy artificial intelligence solutions effectively. Developing and implementing artificial intelligence solutions in healthcare can be costly, particularly for smaller healthcare organizations. The cost of acquiring and maintaining the necessary infrastructure, hardware, and software can be prohibitive. Taken with that healthcare is a complex and conservative industry, and there are resistance to change and adoption of any new technologies, including artificial intelligence. And it may take time for healthcare providers to fully embrace the potential benefits of artificial intelligence and to integrate it into their clinical workflow. I'm going to start off by spending some time on definitions, since computer science is not in our collective vocabularies usually. We are going to learn about machine learning, and then I'm going to continue to clinical artificial intelligence, the clinical application of artificial intelligence, and going to evaluate our current practices and going to explore its use in healthcare. Start with definitions. And artificial intelligence is a broad field of computer science that aims to develop intelligent machines that can perform tasks that usually require human intelligence, such as learning, problem solving, decision making, and perception. The idea that we can get machines to think is an old one, actually. In 1950, Alan Turing was the first to conceive that computers can be used to mimic intelligent behavior and critical thinking. He was a computer scientist, cryptanalyst, mathematician, and a theoretical biologist. During the Second World War, Turing worked for the British government as a codebreaker, and he was there to help crack the German Enigma code. Well, in cracking that code was crucial to the Allied victory. After the war, he continued to work on computers and artificial intelligence, and he is credited with designing the first computer capable of storing and running programs. For coining the term artificial intelligence, unfortunately, did go to somebody else. And in 1956, John McCarthy coined this term, artificial intelligence, and he denoted it as the science of engineering of making intelligent machines. Artificial intelligence began as simple if-then rules that has advanced in subsequent years to encompass multifaceted and composite algorithms that perform similarly to the human brain. Nowadays, artificial intelligence represents an emerging and rapidly evolving model that involves different scientific fields. Artificial intelligence involves various subfields, including machine learning, natural language processing, robotics, and computer vision. Machine learning is a subset of artificial intelligence that focuses on teaching machines to learn from data automatically without being explicitly programmed. Machine learning algorithms use statistical models and optimization techniques to identify patterns and relationships in data and improve the performance over time based on feedback. Machine learning methods enable computers to operate autonomously without explicit programming. Machine learning applications are fed with new data, and they can independently learn, grow, develop, and adapt. Machine learning derives insightful information from large volumes of data by leveraging algorithms to identify patterns and learn in an iterative process. Machine learning use computation methods to learn direct from data, and that is done instead of relying on predetermined equations that may serve as a model. Performance of machine learning algorithms adaptively improves with an increase in the number of available samples during the learning process. While machine learning is not a new concept, it dated back to the Second World War when the Enigma machine was used, as you can see on the picture here. The ability to apply complex mathematical calculations automatically to growing volumes and varieties of available data is a relatively new development. Machine learning makes use of a panoply of data types, either alone or in conjunction with each other. The degree to which data must be pre-processed for machine learning varies depending on the model being used and the research or clinical question that is asked. After preparation, data sets are split into training data and testing groups. A model is generated with training data and subsequently used to predict outcomes associated with test data. This process can be iteratively repeated to improve model performance. After generating the model, several steps need to be taken to make the model practically useful. Machine learning models can be classified as supervised or unsupervised according to the desired output. As models are trained, their predictions are compared with the labeled outcomes. Training process iteratively refines it, aligning predictions and labeled data. In unsupervised learning, correct labels are not present. Instead, models are tasked with identifying similar phenotypes such as patterns of gene expression or putative disease subcategories in unlabeled data. These clusters require appraisal by individuals with specific domain knowledge to establish whether they are meaningful or spurious. Supervised learning is machine learning, as this machine learning approach you can see here on the left, that is defined by the use of labeled data sets. These data sets are designed to train or supervise algorithms into classifying data or predicting outcomes accurately. Using labeled inputs and outputs, the model can measure its accuracy and learn over time. Supervised learning can be separated into two types of problems when data mining is conducted. One is being the classification and the other one regression. Classification problems use an algorithm to accurately assign test data into specific categories, such as separating apples from oranges, or in the real world, supervised learning algorithms can be used to classify spam in a separate folder from your inbox. Linear classifiers support vector machines, decision trees, and random forests are all common types of classification algorithms. Regression is another type of supervised learning method that uses an algorithm to understand the relationship between dependent and independent variables. Regression models are helpful for predicting numerical values based on different data points such as sales, revenue, projections, or for a given business. Some popular regression are linear regression, logistic regression, and polynomial regression. In supervised learning, the algorithm learns from the training dataset by iteratively taking predictions on the data and adjusting for the correct answer. While supervised learning models tend to be more accurate than unsupervised learning models, they require upfront human intervention to label the data appropriately. For example, a supervised learning model can predict how long your commute will be on the based on time of day and weather conditions and so on. But first, you have to train it to know that rainy weather extends the driving time. Unsupervised learning models, in contrast, work on their own to discover the inherent structure of unlabeled data. Note that they still require some human intervention for validating output variables. For example, unsupervised learning model can identify that online shoppers often purchase groups of products at the same time. However, a data analyst would be needed to validate that it makes sense for the recommendation engine to group baby clothes with an order of diapers, applesauce, and sippy cups. Unsupervised learning, seen here on the right side of the slide, uses machine learning algorithms to analyze and cluster unlabeled data sets. These algorithms discover hidden patterns in data without the need for human intervention, hence the term unsupervised. Unsupervised learning models are used for three main tasks: clustering, association, and dimensionality reduction. Clustering is a data mining technique for grouping unlabeled data based on their similarities or differences. Association uses different rules to find relationships between variables in a given data set. These methods are frequently used for market basket analysis and recommendation engines, like the one that you frequently encounter online is customers who bought this item also bought. Dimensionality reduction is a learning technique that's used when the number of features or dimensions in a given data set is too high. It reduces the number of data points to a manageable size, while also preserving the data integrity. The main difference between supervised and unsupervised learning is that labeled data is being used for supervised and unlabeled for unsupervised data searches. The phenomenon that you encounter when you look at machine learning is the presence of neural networks. And neural networks is some of the most prolifically and fruitfully used machine learning algorithms in the last 5 years. The design of neural networks reflect their namesakes. They relay data along layers of interconnected nodes, or so-called neurons, to an output at the end of the network. A layer of input, nodes gather source material such as text, images, or numerical data, and subsequent hidden layers relate to data to one another, creating more abstract, non-linear representations of source data. The output layer is mapped to a desired output. The number of layers in a network can be arbitrarily large. The phrase deep learning refers to any neural network with more than one hidden layer, though in practice, dozens or even hundreds of layers are used for deep learning. Traditional neural networks are most commonly used in computer vision, the use of computers to recognize and extract information from images. Convolutional neural networks are loosely modeled on biological vision with layer that's being can't say analogy to retinal photoreceptors feeding basic information about pixel density into the network. Subsequent hidden layers create successively higher level representations of these raw data, from basic lines and edges to shapes and textures to deeper layers that represent more complex objects such as faces. Convolutional neural networks have application in many medical disciplines. In radiology, neural networks have been studied in also diagnostic tasks such as chest X-ray interpretation and lung nodule classification, and in some otherwise tedious tasks associated with radiology. In pathology, convolutional neural networks have approached or achieved human-level performance in classifying tumors, detecting nodal metastases, and even predicting molecular features. In 2018, a convolutional neural networks-based system for retinopathy detection met prospective defined criteria for clinical use, and that resulted in US FDA approval. Recurrent neural networks have emerged as a powerful means for processing sequential information. Recurrent neural networks are designed to remember previous inputs from a sequence, which in turn guides how they process subsequent inputs and give recurrent neural networks a sense of context. This leads to improvement of their performance on sequential data. And for tasks that include multiple data sources, such as electronic health records, recurrent neural networks provide a flexible framework for processing irregular information. Work published in 2019 has used recurrent neural networks to integrate electronic health records data into predictions of inpatient mortality and acute kidney injury. In addition to recurrent neural networks, embeddings, which represent words and their relations to one another in a multidimensional space, are used in most clinical natural language processing research that has been done over the last 5 years. In the last 3 years, the advent of an additional neural network structure transformer models has led to breakthroughs in handling unstructured text. Collectively, these advances represent an important step toward extracting additional value from the wealth of information in medical records. I'm just going to look next at factors that can potentially limit the utility of machine learning or artificial intelligence in healthcare. Now, the first thing that we must remember is that the source data and the quality of the source data is of paramount importance. Because as with traditional statistics, machine learning systems are only as good as their source data. In some cases, the source data used to develop a model might contain substantial intra-observer and intra-institutional variability. This makes it difficult to establish a gold standard against which the model's performance can be gauged. In such cases, the absence of a reliable reference standard limits the model's reliability. Establishing accurate labels for data might require more effort. Most machine learning-based studies are done in single institutions and based on the single institution's data sets. And this leads to substantial potential for the limitation of the findings based on this data in terms of generalizability. Factor that needs to be taken into consideration is interpretability and accountability. Medical decision-making entails weighing complex and often contradictory data, and clinicians are expected to have sound justification for their decisions in the face of ambiguity. Patients cite a perceived absence of transparency as a source of concern regarding machine learning-assisted medical care. And if machine learning systems become embedded in clinical practice, they will need to be interpretable by both the clinician and the patient. Interpretability is also a safeguard against bias. If a system's biases are accidentally incorporated into a machine learning model, then it's preferable to have a transparent model whose biases can be easily detected and rectified rather than an opaque one whose biases become evident only after they have caused harm. The architecture of many machine learning models is designed with performance rather than interpretability in mind. And this contributes to this perception that machine learning it's a big black box. The ability to convey a degree of uncertainty about a model lends another dimension of transparency. Performing cross-validation and describing a range rather than a point estimate of performance metrics, researchers can more accurately convey how their models perform in the aggregate. Machine learning systems have both intrinsic performance characteristics and characteristics that are affected by the population in which they are being used. These characteristics influence how a particular tool is used, like for screening or as a means of making a definitive diagnosis. These characteristics also merit consideration when there are differences between the population used to develop a tool and the population in which it's ultimately used. Accuracy is a frequently used performance metric, but it needs to be interpreted judiciously, especially in cases of class imbalance, like data sets in which one outcome is more prevalent than the other. For example, in a population with a disease, which a disease is present in 5% of individuals tested, a test for that disease could achieve 92% accuracy by simply assigning positive prediction to 5% of tested individuals at random. This showing the limitation of accuracy as a performance metric. Many predictive tasks in medicine, especially those related to uncommon outcomes, are prone to the same pitfalls. Precision, I think, and sensitivity are two better metrics to evaluate the performance of a test. Clinical artificial intelligence is anticipated to offer new abilities in clinical decision support, diagnostic reasoning, precision medicine, clinical operational support, and in clinical research. Machine learning techniques are used in various sets of areas of health. Artificial intelligence is becoming an indispensable factor to augment decision-making. Artificial intelligence cannot replace the clinician in patient care, but thus those who do not adopt artificial intelligence may be left behind. The perspective of practicing clinicians, machine learning ability, substantial progress carries potential implications across the scope of practice, including diagnosis, risk stratification, and prognosis, treatment planning, and advances in precision medicine approaches. This table consists out of the representative artificial intelligence studies in malignant hematology publications, and these shows machine learning shows promise, both in doing existing tasks and making richer use of existing data than traditional statistics. Artificial intelligence has been widely used in various medical fields, such as image diagnosis, pathological classification, selection of treatment schemes, and prognosis analysis. We are going to touch on the application of machine learning and artificial intelligence on morphology, flow cytometry, omics data, and say a few words about artificial intelligence and clinical decision support systems in oncology. This peripheral blood smear shows red and white blood cells. This shows neutrophils that are labeled in yellow, characterized by multiple lobes. The cells are tasked with the function of finding and destroying bacteria in the bloodstream. The green arrow points to a basophil that protects the body from intruders like bacteria and parasites. Previous approaches to processing hematopathology data entailed identifying and segmenting cells, algorithmically extracting features from them and using these features for classification. In the last 5 years, deep learning models have been able to directly do feature extraction and classification with minimal feature engineering. Accurately categorizing leukocytes and peripheral smears is a task that ordinarily demands considerable time and expertise, has been done by convolutional neural network models with greater than 95% accuracy for most cell lines, leading only to this classification when you have lineages that look similar, such as lymphocytes and reactive lymphocytes. Sorry, yes, that's it. This one. Machine learning's diagnostic abilities extend to accurate classification of diseases such as acute myeloid leukemia and accurately differentiating between myelodysplastic syndromes and aplastic anemia. In resource-constrained environment, convolutional neural networks could be valuable for triage and referral. And it's useful, something for which proof of concept was given in a 2018 paper. And this 2018 paper is describing mobile devices for lymphoma detection. And it is also for these diseases that have high rates of inter-observer variability, like among non-experts, when you diagnose myelodysplastic syndromes. Predictions based on machine learning might provide an additional data point to consider when disagreement or ambiguity occurs. In such cases, the need to establish a reference standard poses a conundrum because it reduces confidence in the labels used to train the machine in this place. By the way, on the right half of the slide, it's 2 megakaryocytes in a patient with 5q minus syndrome. And then obviously on the left is an acute leukemia. Counts and differentials from peripheral blood smears or bone marrow biopsies provide additional information for diagnosis based on machine learning. This information can entail diagnosis or differentiating between diseases such as chronic lymphocytic leukemia and peripheral lymphomas on the basis of blood counts. Work has also shown the utility of integrating blood counts with other clinical and genomic data and clarifying diagnosis, such as with the different diagnoses and diseases leading to bone marrow failure, as you see on the left-hand slide. There's a case of aplastic anemia. Flow cytometry and mass cytometry can also be analyzed with high accuracy by machine learning. And detection of minimal residual disease on multicolor flow cytometry is traditionally done by hand. But by use of machine learning techniques, this process can be automated, with authors reporting human-level diagnostic accuracy in the setting of minimal residual disease detection for acute myeloid leukemia. Similar abilities to detect rare subsets such as minimal residual disease using mass cytometry have been shown with the neural networks. Living beings, genetic information in the cells flow from DNA to the mRNA to protein, and this is dictated by the central dogma of molecular biology. This flow of information is often considered analogous to a computer system which should facilitate the understanding of biological information processes. The study of DNA, mRNA, and proteins is broadly noted as genomics, transcriptomics, and proteomics. The genetic blueprint of a cell is explored using genomics, and it looks at the DNA and helps us to investigate the presence or absence of certain genes. Transcriptomics studies the transcribed genetic material and examines the genes which are actively expressed and provides information about what is happening at the cellular level. Proteomics help in characterizing the information flow. The development of modern high-throughput omic measurement platforms, it has become essential for biomedical studies to undertake an integrative approach to fully utilize the data to gain insights into biological systems. Data from various omics sources can be integrated to unravel the intricate working of systems biology using machine learning-based predictive algorithms. Machine learning methods offer novel techniques to integrate and analyze the various omics data, enabling the discovery of new biomarkers. These biomarkers have the potential to help in accurate disease prediction and patient stratification and the delivering of precision medicine. Precision medicine is motivated by the goal of a better understanding of patient-specific disease biology to devise personalized and rationally selected treatments. Diseases such as chronic myeloid leukemia and acute promyelocytic leukemia are held up as the motivating examples of how elucidating the drivers of a disease can revolutionize its treatment and outcomes. But most malignancies are driven by more complex factors, and thus similar successes have been elusive. As technologies such as next-generation DNA and RNA sequencing become more affordable, it becomes increasingly feasible to obtain personalized data about complex diseases. And very often, data from omics leads to data-rich, information-poor conundrums, wherein a large volume of data is collected, but little clinical actionable information is obtained. Machine learning's usefulness in untangling data has been shown in several settings. In proteomics, machine learning models have successfully diagnosed multiple myeloma via mass spectrometry by use of only peripheral plasma. In the context of genomics, RNA-seq has been used to accurately identify gene expression signatures predictive of complete remission after induction chemotherapy for acute myeloid leukemia. Machine learning has also been used to predict sensitivities to different therapies in acute myeloid leukemia on the basis of next-generation DNA and RNA sequencing and in vitro drug sensitivity. Similar strategies have been used to predict chemotherapy sensitivity in lymphoma, and models such as these might ultimately allow oncologists to adopt a more personalized, data-driven approach to treatment selection. An average adult makes about 35,000 decisions daily. The majority of them are trivial choices about clothing, food, or other things that, no offense, don't really matter. But everything changes as we enter healthcare, the healthcare field, where the right decisions save lives, while the wrong ones lead to grave consequences. Clinical decision support system is intended to improve healthcare delivery by enhancing medical decisions with targeted clinical knowledge, patient information, and other health information. I'm back. The first clinical decision support system was called MySyn was built in the early 70s at Stanford University. It employed an artificial intelligence model that applied over 600 rules to identify infectious diseases, and recommend a course of treatment. Though mycin outperformed medical staff in evaluation accuracy, it was never put to practice, partially because of slow performance, mainly due to the ethical and legal issues. The very idea of the computer acting as a medical expert was too far ahead of its time to be accepted. Nowadays, hospitals use clinical decision support systems for numerous tasks, from generating alerts to drug control to ordering tests. Decision support solutions come in a number of versions, and they can either standalone tools or integrated as part of larger infrastructures such as an electronic health record or a computerized provider order entry system designed to replace paper-based ordering processes. And some of them focus on a single problem and perform simple functions like sending reminders. Others cover a wide variety of processes and include multiple modules. But no matter the size, modern systems benefit from powerful computing engines, cloud technologies, and advanced algorithms. But at the architectural level, they haven't changed much over the last few decades. They're preserving structures similar to early solutions. Typical clinical decision support system contains three core elements: a base of data management, base or data management layer, an inference engine or processing layer, and a user interface. The data management layer combines a clinical database that stores information on diseases, diagnoses, and lab findings, patient data, and a knowledge base in the form of if-then rules or machine learning models. An inference engine or processing layer applies rules of algorithms and data sets from on data sets from knowledge base. You get, well, broadly speaking, two kinds of clinical decision support systems. The one is a knowledge-based clinical decision support system. And these systems of this type are built on top of a knowledge base in which every piece of data is structured in the form of if-then rules. For instance, if a new order for a blood test is placed and then the same blood test was made within the past 24 hours, then duplication is possible. The inference engine runs the built-in logic to combine the evidence-based rules with the patient's medical history and the data on his or her condition. Results come in the form of alerts, reminders, diagnostic suggestions, and a series of treatment options or ranked lists of possible solutions. Non-knowledge-based clinical decision support systems is the core difference between these two. The non-knowledge based are basically consist of applying machine learning models rather than consulting with a library of predefined if-then rules. Such a system learns from past experiences and finds patterns in historical data. These are two techniques most widely used in the two techniques most widely used in clinical decision support systems are genetic algorithms that basically they change from generation to generation to better fit the environment. Genetic algorithms adapt to a new task, producing a number of random solutions and then iteratively evaluating and improving them until the most fitting option is found. The other kind of the clinical decision support system that is not knowledge-based would be also sourcing artificial neural networks. And these networks mimic human thinkings, similar to human brains. Artificial neural networks have a set of neurons called neurons, and they are linked to each other with weighted connections that act as synapses, transmitting signals across the neural network. Non-knowledge-based systems come with the promise to significantly cut healthcare costs and relieve the pressure on medical experts. However, there are issues preventing their large-scale adoption. These include a computation-intensive and time-consuming training process, and the requirement of large data sets need to improve the accuracy of the models. The main obstacle with these systems is the lack of interpretability, as systems can't explain the reasoning behind generated decisions. Clinical decision support systems, major areas of application include we started with the human brains are prone to error, especially when dealing with large volumes of information in a high-stress hospital environment. Computerized systems can take a laboring order of sifting through the tons of data and making countless comparisons to narrow down the number of possible decisions from hundreds and thousands to just a few. Statistics show that 7,000 to 9,000 US patients die every year because of medication errors. Besides that, a lot more people suffer from complications caused by inappropriately ordered medication. Ill-judged dosage or drug incompatibility increase the treatment cost to over $40 billion a year. The decision support tool comes in handy, eliminating the risks from human factors like distraction that accounts for around 75% of medication errors. And using critical patient data such as weight, age, allergy status, and current prescriptions, clinical decision support systems may automatically deal with the following tasks. They can do drug allergy checking, basic guidance, provide basic guidance on dosage, and they can check for duplicate therapies. And they can also perform a check for drug interaction. The drug's interaction with other substances may change its expected effect, and based on clinical documentation at hand, a clinical decision support system considers interactions of newly prescribed medications with there are many computer provider audit entry CPOE systems come equipped with drug safety components that may perform the duplicate therapy and drug dose checking, but you may find separate decision support models to complete existing software. Example of single task solution is a drug allergy checker or PEPID. Clinical decision support systems can provide diagnostic support for disease identification, and these systems are called diagnostic decision support systems, DDSS, or medical diagnosing systems, and they compare information on a patient's condition with a knowledge base and generate a list of possible diagnoses. A specific example of diagnostic decision support system is a solution utilizing deep learning for diagnostic imaging. Traditionally focus on a specific problem area, say lung abnormalities of a particular type or cancer, but similar to other clinical decision support tools, AI-fueled programs work as a second pair of eyes and make suggestions and alerts rather than come to a final conclusion. Clinical decision support systems are used also in cost containment, where the They are integrated into the clinician point of order entry system, and decision support tools may decrease treatment costs by suggesting a cheaper drug, alternatives, or spotting test duplication. Studies have revealed that clinical decision support systems save hospital units hundreds of thousands of dollars per year by alerting to cases of excessive medical testing. Some clinics employ decision support software to enhance adherence to clinical guidance. Similar to information about drugs and diseases, hospital rules can be encoded into a knowledge-based clinical decision support system in the form of an if-then-else piece of information. Such solutions perform various tasks, from prompting nurses to take specific measurements according to a protocol, to informing doctors about the patients who didn't follow their treatment plans. No matter the primary declared reason for implementation, all clinical decision support systems are built with a matter of course intention to cut healthcare costs while improving patient safety. Just going to say a few words about the clinical decision support systems that are used abroad in oncology. Demonstrate the principles applied in establishing a clinically relevant system. There are several clinical decision support systems that are specifically used in the practice of oncology. And as with most machine learning-based systems, the knowledge base remains of prime importance. Knowledge base is constructed by the key and prognostic information in the structured medical records, literature, and guidelines. And a search engine is then used to filter the best results from the knowledge base through key information and feedback to the doctors. The doctor could make a clinical decision based on the clinical decision support system suggestion, or they combine that suggestion with their own clinical experience and prognostic information. And this should be studied form a positive cycle. Artificial intelligence technologies allows computers to simulate human reasoning, thinking, collect, and express the learned knowledge content by generating suggestions and reducing the dependence on memory. The decision error rate and response time, this leads to better, it also helps the clinician to make reasonable and safe decisions to ensure clinical safety, quality, and to improve treatment efficiency. Based on the working principle, clinical decision support has several characteristics. First, the development, the knowledge base of the clinical decision support system mainly comes from big data of clinical guidelines or case composition included in high-level clinical research. Secondly, for the clinical decision support system developed data based on if it's based on a guideline, well, convenience is great, but it is got less reliability. The other important factor to take into consideration when you work with a clinical decision support system is to also look at the updating speed thereof and the abundance of information sources of the knowledge base, and that can affect the heterogeneity of conclusions between the clinical decision support system and the multidisciplinary team. Clinical decision support can guide inexperienced doctors and interns. Artificial intelligence, machine learning represents a collection of tools that will improve our current practice. Artificial intelligence, machine learning is not here to replace clinicians, but merely to aid them in providing the best care to patients. That's all from me. Thank you.
Thanks, Jan Gert. That was very interesting, and thanks for the very broad perspective you gave. Let's see if there are any comments or questions in the chat. I asked the question earlier whether anybody is using an AI-based clinical decision-making support system in their practice. And I see Dr. Yagla Naidu says, I think GPs that are using Discovery Health's Dr. Connect app integrates sophisticated AI technology to help streamline patients to be seen or referred. Hoping some colleagues in the audience who have used this service can comment. Yeah, maybe someone can comment. I am aware, and I've used the Discovery system where you can input summaries of patients when they discharge from hospital, which helps with the communication between different colleagues, GPs, specialists, etc. But these things do take time and maybe a little bit cumbersome. Jan Gert, can I ask you, how far are we from prime time in terms of computer vision and its day-to-day or practical use in the hematopathology laboratory? The studies and the sensitivity specificity for individual cell identification seems very good. But from your perspective, where are we? You mentioned regulatory issues. I think there are big issues with the FDA. I think they've created a whole unit to look at machine learning and how they can regulate it and approve it and approve its use. Concern is always that black box effect, where you can't know for sure how the AI system made its allocation or decision. So any thoughts on that?
Vernon, one of the things that I love about my job is I get to make diagnoses on drops of blood. You diagnose when you need a single drop of blood, and you make a smear and you diagnose an acute leukemia. What I'm trying to get to is actually, I love the complexity of biological systems. And hematology is that one, well, I don't know other fields. This is one field I know. It is always about the whole picture. It is taking lots of variables, putting them together, and then giving you the diagnosis at the end. And I was looking for clinical decision support for hematology, but I did not find that specifically.
Thanks, Jan Gert. Yes, I agree. And I think from a philosophical standpoint, we are going to be challenged because many of us are doing medicine, I think in part because of the way medicine is structured. Either for some of us, it could be the fact that it's almost like a detective story or a problem-solving challenge or a puzzle. And yeah, with systems that would be coming with predictions or diagnoses without any clear way of knowing how they got there, but they might be very accurate, and knowing when and how we're going to be integrating that, accepting it, hoping that it works, is not going to be that easy. Because and I think let's just go to the chat quickly. Jacques Malherbe says, I think the challenge with biases in the data sets should not be ignored and may have a real impact if data sets are not applicable to your specific population. And I think that is a very, very important point. The validation of the algorithms in new populations, in different populations. And I believe there's also the concerns that if you, what they call overfit a particular AI or machine learning model to your training data set, that you will have even bigger problems in getting it to work in other data sets, and that it can actually make some serious mistakes. So there's this balance between using too much and too little in terms of your model. Please interrupt me if you want to say anything. Otherwise, I'm going to continue with the questions.
Before you get there,
yes,
it is some of these clinical decision support, whatever not else. The one specific one I think of is Watson for oncology, and it is got all these fantastic attributes associated with it. It can import data from whatever not different type of panoply of data, things that all get in. But Watson cannot say what you do for your practice and what is good in Cape Town versus what is good in Los Angeles. And that is also, it reminds you that it's not, all of these systems are not standalone systems. They are, you need to have an experienced operator in order to say, yes, it's a good suggestion. No, this does not gel with good clinical practice. The thing is that we shouldn't trust. It is like and I sometimes sit and I read the laboratory requests sent in by doctors, and I think they have this whole magical idea of the laboratory whereby we manufacture results, and when that is it, it's black and white. But the truth of the matter is something completely different. And I think that we should view AI like we view the lab. It is something that we should use properly for the benefit of our patients.
Absolutely. Someone said before we work on artificial intelligence, why don't we do something about natural stupidity? But maybe it's not so much stupidity as just doing what is expected. And I think one of the points I take from what you're saying is that whenever we send blood or a bone marrow, we also actually referring a patient to a colleague in the lab, and that request should be properly labeled, and there should be clear information on what we're interested in. Great, thanks for that, Jan Gert. Andrew says not using any in general clinic use. The closest we have is a drug interaction checker for hospital-based prescribing, and I would hesitate to call it intelligent. Yeah, I'm a very serious proponent of drug interaction checkers. I love the LexiComp one that is integrated in UpToDate. But what I would really like to see, and this is something that's constantly in my head, is an automated system where you have a multimodal AI where you take the patient's prescription data, and that you've got an automated system that reads that checks dosages, that checks drug interactions like Jan Gert mentioned, and that it all happens in a one-stop way. Prof. Johan Potgieter says deep cytometry has added to the single cell analysis, adding immunophenotyping to cell imaging. Johan, can I ask you, just for my knowledge, what do you mean by deep cytometry? Just update me quickly, or maybe I'm just having a quick gray moment.
It's actually, hi Vernon, everyone.
Hi, Johan.
It's actually where the flow cytometer does not only flow cytometer in facts, but also does imaging of the cells, and it draws in, to the best of my mind, also the molecular aspects of the cell. So it is also a function of AI and machine learning to learn in terms of what the cells are and what they are capable of. So, and I think that that's a very type of non-specific answer that I'm giving you. But I think that that is exactly where we're going to, so that you integrate basically all the different aspects of the cell. And you know, what I've put down later on is pathomics, you know, because we talk about proteomics and we talk about genomics, and everything is omics these days. And you think that that must be a very difficult concept, and it is, because that actually just looks at a wide variety of data that results from the analysis of digital images, basically, and it generates a detailed sort of feature, all of the different features of the tissue, more than that we're just looking at when we do morphology, for example. And I think that's the way that it gets approached. What the approach is in terms of AI and machine learning is that it's going to look at a lot of different aspects and matrices that we are not perhaps paying attention to in the way that it learns and in the way that it predicts. And I think that is exactly what I think the only way for us to be able to, in future, being able to have a handle on this is by basically through AI and machine learning, because that gives you the direction almost to manage the big data that gets created in the process. I don't know how to explain it, but I think that that's exactly it, that we won't be able to deal with it unless we have some kind of a help. Yes.
I was thinking about exactly that this afternoon, where I was just thinking about the timing. AI comes just at the right time, where we're dealing with more and more complex data with all these, you know, genomics, proteomics, metabolomics, etc. Data sets that are far beyond our individual ability to interpret or make sense of. So it's exciting that we have this at this moment. And then also the possibility that through AI one could connect dots that may be very, very far apart. The more specialized our individual areas of work have become, the more we become out of touch with other areas. For instance, I just attended the NATA conference this last week, and one of the sessions we had on Friday morning was called Man and the Machine. The chairperson of NATA is an expert in machine learning as well. And he was showing us data on how one group predicted with great accuracy, with trying to think, but it was like very, very accurate changes on an ECG with actual hemoglobin levels in grams per deciliter. But then coming back to what Jacques says, with the biases and the inbuilt biases, when he tried to replicate the same thing in his own unit, he was unable to do it. So there are two different points here. The one is we will start to see connections being made between completely what appears to us to be independent things, but maybe hidden in available modalities, but also the concern about applying it on a different group without proper validation. Jacques says, important that the user of the system know about pros and cons or limitations. We should probably be teaching medical students the principles of AI. No doubt, 100% agreed. That was, I was thinking the same thing driving home today, Jacques, that we have to bring this into our teaching programs. We've got it here on Deep Dive, but even for undergraduate students, it's going to be very, very important. Johan says lots of new terminology, pathomics, etc., and revised approach in computational pathology spells exponential complexity. The big data that gets created in the process will only be manageable through AI and ML. But at least I really hope and I trust and I believe, and I'm pretty sure that the end result will not be getting rid of doctors, but rather that we as doctors will have to learn how to use these things as our assistants. Our work may change, the way we work may change, but at the end of the day, I still believe that there's going to be a very human face that will remain in medicine. I'm very hopeful of that. Great. That was very interesting comments and very interesting discussion. Any other questions or comments from the floor before we say goodbye? Nothing at the moment. I would say watch this space. I would strongly recommend to everyone, but as this meeting is very much focused on our trainees, I want to really encourage the trainees to keep yourselves up to date on the applications. It's not necessarily, I mean, it's not necessary, I think, to learn to code or to know the detail inner workings of machine learning and AI, but I do think it's useful to know the limitations, to play around with some of these new applications that are already available out there. Many of them are free. And for instance, if you play with ChatGPT or GPT-4, any specialist will realize very quickly that these systems are limited, that they are language models, that they are not the same as human beings, that they hallucinate, that they confabulate, that they do all sorts of things. But on the other hand, they also have very useful sides and features but you need to, it's a good way, I think it's a good idea to work with them now while they are still not so good, to learn not to trust them too much. Sort of maybe a counterintuitive way of doing it, but I really think we need to develop an ingrained, careful, wise, slightly skeptical approach to these things, and never give away our critical thinking in exchange for data being poured out by these systems, because if we don't learn to be a little bit questioning and cynical and critical about them, we're going to become more and more like them, machines and not humans. And I think that's something that's special about us and that makes us unique. And I think the difficulty of replicating the human mind shows you how wonderful we've been made. Great. So with that, Jan Gert, fantastic. Thank you so much.
Thank you, Ronan.
Thanks for everyone who came and spent your time with us today. It's great. A reminder again for those who came late that there will not be a session on next week, Monday, because it's a public holiday. As a future reminder, we never do sessions on public holidays. I know it's not always, there are people from other countries that are not always aware of the public holidays in South Africa, but just keep that in mind. Next week, there will not be anything. I wish you all a wonderful day, evening, afternoon, and we are going to have more sessions like these in the future, I'm sure, and here are things change and evolve and develop, because I think we all need to be very aware of what is coming, but it's also at the same time, I think, very exciting. Great. Have a lovely day. Bye-bye, everybody.